When we think of NASA, we often think of space exploration, walking on the moon, or maybe the Hubble Space Telescope. But NASA is involved with research that extends far beyond that. To find out more, we visited NASA's Glenn Research Center in Cleveland, Ohio, and found that sometimes in order to understand how to put things up in the sky, you have to go deep underground. Today we're at NASA's Glenn Research Center visiting their zero-gravity facility. And joining me today is Eric Newman. Eric, could you tell us a little bit about the history of this facility and what type of research is done here?
The facility operates by first preparing an experiment in one of our 7 drop vehicles. And you can see we have 7 of these large capsules here on the floor. Those are our experiment drop vehicles. Once an experiment's been prepared, we'll enclose the drop vehicle with some covers to protect the hardware. We'll then use our overhead crane, which is right above us, to pick up our release mechanism. The release mechanism is lowered over the drop vehicle to be tested, and the 2 parts mated together are placed here on top of the vacuum chamber. When we do a drop here, we first remove all the air from the chamber so that there isn't any wind resistance or aerodynamic drag acting on the experiment when it falls. So once the experiment's in place and we seal up the vacuum chamber, we can then begin the process of evacuating the chamber. It takes us about an hour to pump the chamber down. We pump it down from 760 torr, which is standard atmospheric pressure, down to a pressure of about 0.1 torr. Once we're at the proper vacuum level from our control room here in the facility, we can power up the experiment. Once the experiment looks like it's ready to go, we'll simply press a button in the control room, executing the process of releasing the experiment. As soon as we let go, like I said, we're weightless, just as if we were on the International Space Station, and the experiment begins. 5.18 seconds later, the experiment has fallen 432 feet and is stopped in a large container of expanded polystyrene beads at the bottom of the chamber. The stop at the end of the fall is pretty abrupt, about 35 Gs on average, but is still soft enough that we don't typically break any of the onboard experiment hardware.
So with the types of forces that would be experienced with that type of deceleration, obviously biological testing is out of the question.
That's correct. We can't do any test subjects or experiments with human or animal test subjects because they wouldn't survive the stop at the end of the fall. So most of our experiments deal with physical processes such as how fluids react to the low gravity environment, how fires burn, combustion events occur in space. Most of our experiments deal with things of that nature.
So there are several different types of zero gravity experiments that can be done. How does this compare to those, and what are some of the advantages and disadvantages of this facility?
As you mentioned, there are several ways to achieve a low gravity environment. Simple free fall in a drop tower is probably the most basic way to achieve a low gravity environment. The next step is the parabolic aircraft, where the airplane follows a roller coaster type path and is in a free fall for several thousand feet. Then you can go into a suborbital rocket flight, where you essentially have a parabolic rocket flight that doesn't go in orbit and returns and can provide minutes of low gravity. They all have their pluses and minuses. Generally, the big advantage of the drop tower is its low cost and its ease of use. There's no big prep time, there's no big crew to prepare a launch vehicle or an aircraft. We can operate this facility with about 6 or 7 people, and we can provide a very high quality, low gravity environment. We've just entered the vacuum chamber at the 420 foot level, so we're about 420 foot below the experiment release point, just above the decelerator cart or catch bucket, which stops the experiment at the end of the free fall.
And how deep is that?
Well, the decelerator cart is about 20 feet in depth. We use about 15 feet of that depth to stop the experiment.
And usually that's filled with the foam pellets.
Right. Typically, when we're prepared to drop, we would be full to the top with that white expanded polystyrene material.
Now that looks like a pretty small diameter. You don't have much margin for error. Does the size of that hole measure with the width of the drop vehicles?
Well, the diameter of the catch bucket is approximately 5 feet, and the experiment vehicles are about 38 inches in diameter, so it doesn't leave a lot of room for error when the drop vehicle enters the decelerator cart.
Have you ever had a miss?
Well, we haven't had a miss while I've been employed at NASA, but I do know of a miss that occurred in the early 1970s. Back then they were using a different style drop vehicle and doing some experiments with fluids research. That particular drop vehicle had a thrust system on board which would simulate a spacecraft thruster firing so that they could see what effect the addition of acceleration had on the fluid in the test article. Well, apparently they had a thruster misalignment which pushed the vehicle slightly off course, and it hit the edge of the decelerator cart, destroying the drop vehicle.
Now, normally when the experiment is running, this chamber is completely evacuated of air down to a very, very low pressure. So we obviously couldn't be standing here if the experiment was running.
That's true. If there was a vacuum in here now, we'd have a hard time breathing. We'd need our spacesuits to enter the chamber.
But under those conditions, that also means that there's no air pressure that can move the vehicle around, so it should drop straight down, right?
That's one of the advantages of the vacuum. We don't have to worry about any aerodynamic effects on the drop vehicle. That's why there's no fins or anything else to keep the drop vehicle falling straight. With the lack of air, the drop vehicle falls straight into the bucket every time.
So I know one of the experiments that you guys are planning on doing this week, I believe, involves having a rotating bell jar inside where the whole experimental apparatus is rotating inside of the drop vehicle. So how do you prevent that from affecting the trajectory?
Well, we do have a drop vehicle which has what we call the combustion centrifuge on board, and rotating that chamber allows us to look at partial gravity environments or how things might burn on the moon or Mars. Rotating that chamber made us a little nervous the first time we dropped it. We are very careful in balancing the drop vehicle and balancing the chamber so that there's no imbalance in the rotation, and we don't accelerate or decelerate the rotation during the drop. And hopefully it hits every time.
So if we could actually take a video of what was happening when the drop vehicle was on its way down, what would we be seeing from inside the chamber?
Well, at the decelerator cart level, we would see the expanded polystyrene appear to boil. That is, it would be bubbling, and that would be due to outgassing of the expanded polystyrene during the vacuum pump down process.
And then when the drop vehicle actually hits the polystyrene pellets, is it the compression of those pellets that slows it down, or is it something else?
It's a combination of the compression of the pellets and the flow of the pellets around the drop vehicle out of the decelerator cart.
I'm being joined now by Dr. Sandra Olson, a research scientist here at NASA's Glenn Research Center, and she's going to be walking us through how the drop rigs are actually prepared and some of the experiments that are conducted. Dr. Sandra, thanks for joining us. Can you walk us through how you prepare these drop vehicles for testing?
Sure. This is the rig that I've been testing with, and it's a microgravity wind tunnel rig that we do low velocity spacecraft atmosphere tests in. And what we do in this rig is we prepare the samples by making up sample holders like this one. And what we do is we create the sample, we hang it in the rig, and the rig is able to create an atmosphere of the pressure, the oxygen, and the flow rate that simulates a spacecraft, especially exploration atmospheres. We've done a number of experiments where we've studied things like hair flammability, for example. If your hair is exposed to elevated oxygen, it burns much better than it does in air. So we've done testing like that to see what we could do to protect the astronauts.
Can you walk us through the experiment that you're preparing now?
Sure. This is the sample holder for an ISS experiment that we're in development. And what we're planning on doing is burning a piece of acrylic sphere, and we've got some thermocouples instrumented on the sample, and we ignite it with a retractable igniter, and once it's ignited and burning, we release it in the drop shaft and study it for the 5.18 second fall. I don't know if you know, but they've had a number of fire incidents in space. The earliest one that happened in space in the US side is Apollo 13. And if you know what happened in Apollo 13, they had a fire in an oxygen tank. And the oxygen tank overpressured and ruptured and caused all the problems that Apollo 13 had. And that was all caused by a fire. On the Mir space station, they had a pretty bad fire with an oxygen generating canister that caused a lot of heat damage and a lot of smoke combustion products that they had to, clean up afterwards and they almost abandoned the vehicle. And so, fortunately, on the ISS, we haven't had any major fire incidents, so we're hoping that never happens. But clearly, in a spacecraft, you can't just leave the building easily and come back and fight the fire. So we want to make sure that the materials we fly are not flammable. One of the things we found during our drop testing is that materials in microgravity actually burn better than they do here on Earth in some cases. And we just demonstrated that on an ISS experiment this past spring, where we burned a material that will not burn in a downward direction on Earth, but we were able to get it to go in the spacecraft in the same opposed flow direction. So we proved that there's a delta on the flammability, and it's not in our favor. It's actually, if you screen a material on Earth and it's okay to use on Earth, and you take it to space, if it's marginal on Earth, it might be actually flammable in space. It's a negative factor of safety on the material's flammability.
Can you give us a little bit of detail on why flammability and combustion is different in a zero gravity environment versus here on Earth? What are some of the factors that play into that difference?
Okay, sure. On Earth, the flame is strongly affected by the buoyant flow. The hot air rises, basically, and that brings in the fresh air behind it, and that feeds the oxygen to the flame. Now on Earth, you have a certain gravity level, and that dictates how strong your buoyancy is. In a spacecraft, there's no gravity, and so the only flow is due to the ventilation, the spacecraft ventilation, because there's always ventilation going generally, or the crew movements. And those are much lower velocities. So if you think about what the flow is doing to the flame, it's actually bringing in fresh oxygen, but it's also cooling the flame, because especially on Earth, there's a lot of buoyancy. And so it's actually cooling the flame, because the flame has to heat all that excess air that it really isn't using for anything except it has to heat it. On a spacecraft, if you have the sweet spot in the flow, which generally that's what the ventilation flows are, they're kind of like the sweet spot for combustion. You can get enough oxygen, but you're not cooling it too much, and so actually the flames actually are stronger because they don't have to waste all that excess heat cooling the excess air.
As we conclude our time here at NASA's Glenn Research Center, we find that the work of the scientists here extends far beyond simply building satellites and launching rockets. They work to make space travel safer, as well as finding ways to make life better for all mankind. Tune in next time as we visit NASA's Stirling Engine Lab and find out about the technologies that will power the spacecraft of tomorrow.